able chair to steer it, who is Dilip Jatkar from Harish Chandra Research Institute. So, I now hand it over to Dilip.
Thank you. So should I wait for a couple of minutes? Maybe.
Sure. Yeah. You should wait. But now it's your decision.
Yeah, sure. Okay, Liam is also around. Okay. Okay, so let us start the third session of today. In this session, there are three speakers, and the first speaker is Cumrun Vafa, and he'll be talking about unifying themes in Swampland program.
Professor Vafa. Share my screen. Thank you very much. Let me see. Are you seeing my screen?
Yes.
Great. So thanks for inviting me to give a talk here in the dual mysteries of gauge theories and gravity in honor of David Gross. So I'm going to talk about some unifying themes that have emerged in the Swampland program in the past few years. So almost all consistent quantum field theory is becoming consistent when coupled to gravity. So this is in some sense related to the theme of the conference, except it's the opposite. They are not dual features, they're opposite features. So quantum field theories seem to be good. I mean, we understand there are infinitely many nice quantum field theories, and what is consistent we understand, or at least we think we understand, but it turns out that almost all of them become inconsistent when we couple them to gravity. And the string landscape suggests that there are only a finite number of quantum field theories that emerge in the infrared limit of consistent quantum gravitational theories. And this is a big surprise. And even though we don't have a proof of this statement, it seems like we have a lot of evidence for this statement. And the Swampland program is, the idea is to try to find conditions which rule out a quantum field theory as not being able to arise in the infrared limit of a quantum gravitational theory. And the basic idea is to use non-string landscape to find such criteria. And the program is most effective if the following statement is true, what we call the string lamppost principle, that all consistent quantum gravitational systems arise as part of the string landscape. This may or may not be true. Again, we have a lot of evidence that this may be true, but and if this is true, then the idea would be that when we are looking at the examples that string theory provides in the landscape, finding common features between them and trying to understand why they are like this, and what is this finite set that we're getting from string theory, what is distinguished about them, could hopefully guide us in understanding what criteria the Swampland criteria should be. And of course, the more we can connect it to basic principles, the more we believe that these ideas are relevant for swampland. For example, if we can have some ideas relating them to principles such as unitarity of black hole physics, or holographic principles, or such things, if we can connect them to some other ideas, then we can begin to gain even more belief in the statements. Now, another example among the string landscape, which has been very helpful in this connection, is the supersymmetric landscape. Even after so many decades of research in string theories, it's still fair to say that our basic guiding principle about string constructions involve supersymmetric cases. We understand those much better. And so supersymmetric landscape is in particular the main cases where we have a lot of examples that we can turn to. Now, this talk will cover the work of a large number of people over several years, close to a few decades now. And here's a very incomplete list. And what I'm going to do, I'm going to apologize, first of all, for any omissions. And I'm not going to give any references to the idea, just to keep the unity of the discussion going forward. And this is really a collective effort by the whole community. And I think the more useful thing I could have done in this talk is to basically give what are the themes arising. And that's what I'm going to be doing. So what I'm going to do is, first of all, go over the various swampland criteria, some of them. I'm not going to be able to do justice to all of them. So I'm going to highlight some of the things that I find particularly interesting. So highlight them, explain where we get them from, why we think these are good ideas. After I go over one by one, I then talk about interrelation between these swampland ideas. What are the connections between them? And then finally, at the end, I will summarize by seeing what kind of unifying themes emerge from all this picture. Again, not only I'm not going to give you all the swampland criteria proposed, I'm not going to give all the relations between them that have been proposed either, just a sampling of them, just enough to get some general flavor of what these ideas are. So perhaps the very first one, and this is more than a few decades old, is the idea that there are no global symmetries in a quantum theory of gravity. And there are various examples that point to this, the various basic ideas that point to this. Unitarity of black hole evaporation is one idea. And in the holographic context, these kind of ideas can actually be derived. These are all point in the direction that there are no global symmetries in a quantum theory of gravity. None of them, I would say, is a complete proof in all cases. So we don't really have a proof, but it's really one of the principles that we really have strongest evidence for and strongest belief in. So no global symmetries in a quantum theory of gravity. The next one is the completeness hypothesis. Completeness hypothesis says that if we have a gauge theory, like say P-form gauge fields, or even the regular gauge field, the spectrum is complete. That means that every charge that is allowed by that gauge theory is actually part of the spectrum. May or may not be stable, but should be part of the allowed spectrum. So that is the completeness hypothesis. And that is, again, we have plenty of evidence for this in all the string constructions. The next swampland criteria I want to describe is the cobordism conjecture. Cobordism conjecture basically says that the cobordism classes in a quantum theory of gravity is trivial. It is kind of motivated from uniqueness of string theory, that if you take a string theory, you can be able to connect it to everything, and in particular to nothing. So if you, for example, have a manifold with some kind of bundles or some fluxes or whatnot, you should be able to get rid of all of them and basically get it to nothing. So in other words, if you look at the projection of the theory that we get in the uncompactified direction, you get a theory which has a boundary. Said differently, cobordism conjecture is a statement that any quantum theory of gravity admits a bubble of nothing, regardless of which quantum gravity you start with. So in other words, you can actually, there's no criteria, there's no physical class or charge which distinguishes a particular string compactification, for example. So again, we have a lot of evidence for this. We look at various kind of string theory examples, and in all these string examples, we find that the cobordism class is trivial. At least in many of them, we have a strong evidence. The next one is the baby universe hypothesis, or I could say no free parameters hypothesis. Baby universe hypothesis is the statement that the dimension of the Hilbert space of baby universe is 1. There's only one dimensional Hilbert space. And this is related to the following statement that in string theory, every parameter that appears in the theory could be viewed as an expectation value of some field or some degree of freedom. And in particular, there are no super selection sectors in string theory. If the dimension of the Hilbert space was more than 1 for the baby universe, as Coleman taught us, you would have alpha parameters, and these would correspond to super selection sectors. And this is not the case in quantum theories of gravity that we are seeing coming up from string theory. And therefore, the fact that we don't expect alpha parameters motivates also that the cobordism, the dimension of the Hilbert space of the baby universe is one-dimensional. Next one I want to discuss is the distance or duality conjecture. The distance conjecture or duality conjecture is probably one of the most powerful principles, I would say, from the way we use them, the Swampland criteria. And the idea that if you have a moduli space of some fields in your theory, moduli space of some scalar webs, if you go to extreme limits in the moduli space, you will invariably end up with a tower of light modes. And so in other words, if you look at the moduli space, there's a metric on it which is dictated by the kinetic term of the scalar fields. If you use that metric to measure distances on moduli space, and if you go infinitely far away, you invariably get the situation that when you go to far enough distance, as you go to infinite distance, you get a tower of states whose mass exponentially goes down with the distance that you traverse, with some exponent which is order 1. Now, this is a distance conjecture, but it also can be viewed as a duality conjecture. It is a statement that the dual degrees of freedom, a duality is going to be describing the far infinite web of these fields, and these light degrees of freedom that are emerging are the degrees of freedom of the dual theory that are describing that dual theory. In other words, the emergence of the light degrees of freedom is signaling to us that our original description is breaking down, and there's another description taking over. And typically, these are weak coupling limits that we are familiar with. So this is, again, something we do not have a good reason a priori why it should have been so. It is really why there should have been dualities in string theory, which we still do not understand after so many decades. But it seems to be the case in all these cases that we have studied or we understand in the context of string theory. So again, this distance conjecture seems to be an important principle, or what we call the duality conjecture. Of course, this could be sharpened by the statement about whether or not we expect this light tower state to be weakly coupled or not, and to say exactly what that means and so forth would be an interesting extension of the distance conjecture. But the distance conjecture in its bare form is just a statement that there's a tower of light states emerging in this way, exponential way. The next Swampland condition is, again, already more than a decade old. It's a weak gravity conjecture, and that's a statement that the gravity is the weakest force among all the forces. And it's motivated by the condition that except for supersymmetric BPS black holes, all black holes decay. And for this to happen, you need to have some entities, some light entities, whose mass as a function of charge is less than or equal to the mass of the extremal black hole as a function of charge. So in other words, the mass as a function of charge should be less than or equal to charge with the suitable coefficients having to do with the extremality formula for the black hole. And this allows you by in this way by the conservation of energy and charge for the black hole to evaporate and get rid of its degrees of freedom. So a sharpened version of the weak gravity conjecture states that equality is only true if you have BPS states, supersymmetric states in a supersymmetric theory. And for any other one, there's a sharp inequality, strict inequality. And then there's also a lattice version of this. In other words, the question is for which charge such a statement is true. And the statement again is that the basic statement is not true that it's true for every charge in the theory. It's true for some charge, but not some large charge. In other words, some order 1 charge in the theory. And again, what is that order 1 charge? We do not know exactly. What is that order 1 charge? But something of order 1 charge should be satisfying this relation. In other words, something microscopic should satisfy this relation. And the minimum charge for which is true would be very nice if we can actually be able to say precisely, but we don't have this statement for the weak gravity yet. There's also a lattice version of it, which suggests that not only this is true for one of the charges, but it's actually true for a whole lattice in the charge lattice. The next one I want to discuss is the ADS conjecture. ADS conjecture states that nearly flat ADS, there are 2 versions of the ADS conjecture. There's 2 aspects to it. One aspect of it, it says that the nearly flat ADS does not exist. Now, what do I mean by this? You might say that we do have a lot of these examples of ADS CFT holography. So what do I mean by nearly flat ADS does not exist? It is the statement that if you try to get the near ADS flat limit, you invariably get something else also getting large. In other words, ADS is not alone. You could have the near flat limit of ADS multiplied by something which becomes, curvature goes to 0. For example, if you have ADS 5 times S5, you can make ADS 5 nearly flat at the expense of S5 becoming large. So you never get ADS really. You have this extra baggage with it. So it's always higher dimensional. So you cannot have an extra, in other words, you do not have a separation of scales between ADS and the internal space. So in other words, ADS by itself cannot be viewed as a compactification of string theory. Now, the other statement about ADS Swampland conjecture is that while supersymmetric ADS with extra dimensions can be stable, non-supersymmetric ones are unstable. So you cannot find non-supersymmetric ADS vacua in the string theory. And of course, the supersymmetric ones with ADS will have these extra dimensions that condition 1 would suggest. The next one I want to talk about is the de Sitter conjecture. De Sitter conjecture talks about the situation where the energy is positive. So we have a situation where we have a potential as a function of fields, and we are looking for the potential. The de Sitter conjecture suggests that for such situations where you have a positive potential, the slope of the potential relative to the potential is bounded. So general string compactification to 4 dimensions seem to give you a bound of the form I have written down in Planck units. V prime over V, absolute value of V prime over V is bigger than or equal to square root of 2/3, at least in the weak coupling limits. So here phi, as we discussed already, if you take the large values of phi, you're at the weak coupling limit. And in string theory, where we look at weak couplings, we always find a situation where V prime over V is bigger than square root of 2/3. And this is basically suggests that we always have a potential which goes like e to the minus some constant times phi for phi much, much bigger than 1. We do not have it. So the de Sitter conjecture is basically motivated from such examples in string theory. And it suggests that what's called the refined de Sitter conjecture suggests that V prime, this slope is bigger than a constant times V. And the minimum of the V double prime is less than minus C prime times V. In other words, this criteria forbids a metastable, so it's either or. So in other words, either V prime is bigger than CV, for which V prime is never 0, or if V prime is 0, which means that you might look for de Sitter, then the minimum of V double prime is less than minus CV prime. In other words, it's unstable. It's highly unstable, so it's not really a stable situation. So it's so this basically gets rid of metastable de Sitter vacua if this conjecture is correct. Then there's this Transplanckian censorship conjecture. The Transplanckian censorship conjecture. So not unrelated to this, I'll come back to it. one might have asked, what is the connection of the distance de Sitter conjecture to something like black hole or some more fundamental properties of quantum gravity? Where does that connect to anything? And the Transplanckian censorship is trying to put some kind of a rationale. So it assumes that in an expansionary background, sub-Planckian fluctuations cannot grow to cross the horizon and freeze out. So anytime you have a sub-Planckian degree of freedom in an expansionary universe, you cannot have a situation that you expanded enough by A final over A initial so that the L Planck becomes bigger than the horizon size at the final point. So it always should be bounded by this. This is the Transplanckian censorship conjecture. Again, I will talk about the kind of motivations other than the fact that this sounds at least some kind of a rationale into this, and what kind of things it implies I will mention later when I talk about the relations between various conjectures, and in particular its connection to the de Sitter conjecture. Finally, I want to talk about the finiteness hypothesis. The finiteness hypothesis is basically is a hypothesis which suggests that we only have a finite number of vacua. Now, just to elaborate what this would mean, first of all, if you have a supersymmetric vacuum, you could have a web of fields changing. So you have a continuous web. So you could say, well, that's already infinitely many vacua. So what I mean by finiteness, I mean finite families of vacua up to these moduli deformations. So for example, it's a conjecture by Yau that the number of Calabi-Yau is finite. The number of Calabi-Yau being finite in any dimension, it already gives you the situation that all these constructions that we have in string theory to get supersymmetric background will be finite number of them. So the finiteness hypothesis, again, does not have a priori any direct rationale from basic facts like unitarity and so forth, but it's an observational fact about the properties that the string landscape seem to enjoy. Okay, so these are basically the only criteria of Swampland's criteria I want to describe today. Now I want to talk about the connection between various connections between these conjectures. Before I do that, let me just give you an example of the finiteness hypothesis. The landscape of, as I said, this is finite, and I just give you one example of the finiteness. So finiteness, and this we have connected it to other principles. We have derived this from connecting to the distance conjecture, for example. For theories with 16 supercharge, the rank of the gauge group is bounded by 26 minus d. This is the thing we have observed in string landscape, but actually we have an argument based on string duality and based on the distance conjecture and the ideas of completeness of BPS spectrum that this holds. So this is an example of this finiteness, whereas you would have had infinitely many possibilities for the rank of the gauge group. There are only finite number of them realized, at least when we have enough supersymmetry. Okay, now I come to the various connections between these criteria. So first I want to talk about the various connections between the global symmetries, no global symmetries. It connects to the ideas of completeness, cobordism, baby universe, distance, and weak gravity conjectures, and let me explain how. So no global symmetries is very closely aligned with completeness. If the spectrum is not complete, we get higher form, perhaps global symmetries. And this is not complete, the story, because there's some discrete cases or non-abelian cases that this doesn't cover, but it at least gives you a connection between the completeness of the spectrum and the global symmetries. So in many cases, these completeness follows from the absence of global higher form symmetries. Cobordism conjecture already implies that there are no global symmetries. In other words, if you did have global symmetries, then you can label the corresponding cobordism classes with those charges, and they would be non-trivial cobordism classes. You cannot go from one to the other, and therefore this would violate the cobordism conjecture. So cobordism conjecture already implies that global symmetries do not exist in quantum gravity. Baby universe hypothesis similarly implies that global symmetries are forbidden because it will lead to multi-dimensional baby universe Hilbert spaces. The global symmetries can be labeled the charges of the compact baby universe Hilbert space, which is not possible if there were gauge symmetries, which would have been trivial. So global symmetries are forbidden if the baby universe hypothesis is true. Now, there's a relation also between the no global symmetries and the distance conjecture. So in certain cases, global symmetries imply mass spectra cannot depend on moduli. And this would contradict distance conjectures. For example, like axionic physics and so on would be related to such an example. This is some weak relation here. And then weak gravity conjecture is probably more directly related to no global symmetries. Weak gravity conjecture basically says that if you want to make a gate symmetry as weak as you want, make it weaker and weaker and weaker to become basically a global symmetry, you hit an obstruction. Namely, if you fix the charge spectrum, and if you try to take the limit of zero coupling in order to make them a global symmetry, it will lead to inconsistency because of the weak gravity conjecture, because mass should be less than the charges, and if you take the charges to zero, that will violate that condition, unless you take also the masses to zero. And for example, the lattice version of the weak gravity will tell you that there's infinitely many massless light states, charge states, if you do that, and that would be a tautology. So this is basically the kind of problems that the connections that the no global symmetries connect to. So it connects to various other Swampland conditions like this. So I talked about no global symmetries, and let me talk about the connections between the cobordism and these some other ones, between the completeness hypothesis and the baby universe hypothesis. Again, if the spectrum is not complete, cobordism classes cannot be trivial, and this is something I already mentioned. And baby universe hypothesis, it's related. Sorry, this is not what I mentioned. I mentioned the no global symmetries, but this is closely related to the completeness hypothesis. So, for example, if a d-brane of a given chart doesn't exist, that leads to cobordism classes. So the cobordism triviality already gives you completeness of the spectrum. Baby universe hypothesis also relates to this. Namely, if you have an incomplete spectrum, leads to global symmetries and thus to multi-dimensional universe Hilbert space. So you have some kind of the completeness of it is guaranteed by this. I then talk about the distance or duality conjecture. So we have connected these together. These are all related. The distance conjecture is one of the powerful ones, actually. It connects to all these nearby ideas. And so let me try to describe it, some of these connections. So perhaps I should start with so first of all, the trans-Planckian censorship conjecture. You see, in the distance conjecture, there's an exponent. We say that the masses of the light star is less than or equal to e to the minus some constant times phi, but we haven't said what that constant is. It says order one constant. It turns out the trans-Planckian censorship conjecture would provide the actual constant for that distance conjecture. It turns out that trans-Planckian censorship conjecture will tell you that the masses involved should be less than e to the minus alpha phi, where alpha is 1 over square root of d minus 1 times d minus 2. So this quantifies the growth rate. So this order 1, which is this mysterious order 1 number, becomes very specific, that mass is always less than or equal to this exponent. I have to here make a comment that Swampland criteria typically talk about the situation where we have the regular Einstein theory of gravity. So the dimensions 1 and 2 are topological in a sense. We don't really have the regular Einstein's theory. So many of these criteria I'm talking about do not apply to dimensions like 1 and 2. For example, no global symmetries is not true in 2 dimensions. You could have 2D quantum gravity, which has global symmetries. So this is also reflected here in the fact that in this exponent, you get this d minus 1 and d minus 2. I'm talking here about dimensions bigger than 2. Dimensions 3 is sometimes a borderline, but at any rate, so certainly dimensions bigger than 3, we will think about these conditions. So this mass is less than or equal to this exponent is a prediction of TCC. Now, weak gravity conjecture is also related to the distance conjecture, because as we said, there are no free parameters in the quantum theory of gravity. So coupling constants are also dynamical. And when you look at the coupling constants, you find that the coupling constants grow with distance exponentially. In other words, the coupling constant value is e to the minus alpha or some constant times the distance.
Sorry, I was instructed to interrupt you. This is not my initiative. How is phi normalized here?
Phi is normalized by the kinetic term. So here, what I mean by this,
normalize
the distance in phi space. Sorry?
But if you have several different phis.
Yeah, so it's a distance. So in other words, that means that if you take any point, and if you go to far enough distance and take a geodesic length, that's what I mean by phi.
I see.
So it should have been d of phi, the distance in phi space, if you want to be more precise. So the weak gravity conjecture here will be saying that the couplings grow exponentially with distance. So g goes like e to the minus some constant times distance. And since the mass is less than or equal to the coupling, according to the weak gravity conjecture, it will give you this relation that the mass is exponential, less than exponential minus a times the distance. So again, this is relating the distance conjecture with the weak gravity conjecture. There's also a relation to the de Sitter conjecture. The tower of states, so de Sitter conjecture, the distance conjecture tells you that there's a tower of states. The tower of states that's getting lighter and lighter. But if they get lighter and lighter, they increase the Hilbert space. And the fact that the entropy of a quasi de Sitter space goes like 1 over the cosmological constant or 1 over the potential, if its potential is not varying very fast, gives you a relation by this following. Since the mass is less than e to the minus a constant times the distance, then from this you find that the entropy goes like e to the constant d phi integral, or the potential goes exponential with distance, with some constant, depending on the number of towers. If the towers are growing, you get some condition like this. And so it formally gives you a relation like v prime over v bigger than that constant. So there's this loose connection between the Gibbons-Hawking entropy, the fact that their states are coming down, and the fact that the potential is going down exponentially. And then finally, in the ADS conjecture, I said that there's no separation of scales between the ADS, and this actually can be related to the distance conjecture if you view cosmological constant itself as a web of field. Typically, the cosmological constant is a web of something, is related to the web of fluxes in the ADS CFT context, for example. And so if you think about this as a dynamical field and measure the distance in the cosmological constant space, you find that this leads to a formula of the form that there should be a tower of states, mass, which go like the cosmological constant, absolute value of the cosmological constant, to some power alpha, and alpha turns out to be a half for supersymmetric cases. In other words, if you take an ADS in the supersymmetric context, in all the examples we know, you always get a tower of light state as you go to the nearly flat ADS limit. As lambda goes to 0, you get the tower of light states, and that is given by this formula. So alpha is, we know it to be a half for the supersymmetric case, in all the examples we know at least, and it's nearly flat in the ADS, and this in general basically is related to the nearly flat ADS condition in the Swampland. Excuse me. So that was for the distance conjecture. Now I talk about the connections between the weak gravity and other ones. I've already talked about the connection with the distance conjecture and the no global symmetries. I'm going to talk about the connection between the weak gravity conjecture and de Sitter and ADS conjectures. So ADS conjecture connects to weak gravity because non-supersymmetric ADS, so one of the ADS conjectures was non-supersymmetric ADS is unstable, assuming the strong version of weak gravity conjecture. The strong version of the weak gravity conjecture is telling you that you don't have the mass, or the more generally the tension of brains is less than their charge, and there's strictly inequality when it's not supersymmetric. So if you stack along the parallel brains and trying to get ADS, you find that the tension being less than charge means that they repel each other, these branes. So non-supersymmetric branes repel each other because their tension is weaker than their electric repulsion, and therefore we should not have any non-supersymmetric stable ADS Vacua. And this seems to be the case that in many of these examples that people attempted to construct non-supersymmetric ADS, they always invariably seem to find the decay mechanism of this domain wall, which basically peels off brain after brain in such a way that it depletes the flux of these ADSs. Again, this is not a proof that they are related, that they are the same, but gives you an example of how they can possibly support one another. De Sitter conjecture also gets related to weak gravity conjecture. So there's a scalar version of the weak gravity conjecture, which basically says that, so the weak gravity conjecture was motivated by black holes and therefore the extremal condition for charges, but people have suggested extensions of it to the scalar version, where you talk about scalar fields, and that any field, basically any entity, the gravity should be weaker than the corresponding, the gravitational attraction should be weaker than the corresponding forces involved with the objects. So in the case of a mass which depends on phi, the md phi will quantify the charge, and m is the mass. So this is a kind of a scalar version of the weak gravity conjecture. And so this is for a particle, but if you extend it to domain walls or tensions of brains, you get a similar relation for brains, which is this one. And if you take our whole universe as that brain, you're basically replacing that tension with the cosmological constant, or V. And this is basically saying that the potential is less than the slope with some constant. And this is the slope conjecture for the De Sitter. Now I talked about the Transplanckian censorship conjecture. I've already talked about its relation to the distance conjecture. I'm going to talk about its connection to the De Sitter conjecture. The Transplanckian censorship conjecture also connects to some other ones, but I'm not going to talk about all of them. I'm just going to talk about the relation of it to the De Sitter conjecture. So Transplanckian censorship conjecture, in fact, leads to the De Sitter conjecture in asymptotic regions with the specific predictions for the slope. So if you follow the Transplanckian censorship conjecture, if you have a potential which is not growing very fast at the infinity, you get in trouble with TCC. So you find that you need, at least in asymptotic regions, the slope to be bigger than the value of the potential up to some constant. But now again, the constant is quantified. So it's not an arbitrary constant. The constant is 2 over square root of d minus 1 over d minus 2. This is the same kind of exponent we got in the weak gravity conjecture, except that one did not have that 2. So this seems to be an interesting factor. And the De Sitter conjecture implies this. And interestingly enough, in examples that we can construct from string theory, like the square root of 2/3 I told you about in 4 dimension, exactly relates to this bound that I mentioned here. So it's related to this value of C. So it seems like we have found the best bound from this perspective. So and this is one of the motivations for TCC. TCC actually comes up with a very specific slope, which is actually consistent with the best bounds we can get from string theory. Okay, so let's look at what we've got. So we have got all these interconnections between at least these different criteria, between these different Swampland criteria. We have talked about various connections between them. This finiteness hypothesis seems to be a standalone guy here, which seems not to be connected to too many things and to nothing in some sense. But actually, I believe it's actually one of the most basic things, and I really love to understand its meaning. At first sight, you might think that actually it's in contradiction with ADS-CFD, because there are infinitely many CFDs, that much we know, and therefore you would expect there are infinitely many ADSs. This is not in contradiction with finiteness hypothesis, so let me explain what that means. If we could have gotten infinitely many ADSs with internal space to be our decoupled scale, then it would have been a contradiction. So finiteness hypothesis has a connection, at least a weak connection with the ADS conjecture, that you cannot get ADSs, infinitely many ADSs, because there are an infinite number of them. In other words, ADS must have had at least a tag-along extra big space. Said differently, finiteness hypothesis does not say that you cannot have infinitely many branes within a given theory. For example, if you take type 2b string theory in 10 dimensions, you can have arbitrary number of D3 branes in it, n D3 branes. That is not in contradiction with finiteness hypothesis, because there's a finite supergravity in 10 dimensions. There are a finite number of them. Type 2b is one of them. But that doesn't, there are infinitely many degrees of freedom that you can turn on within that theory, like the branes. You can turn on n D3 branes for any n, occupying a finite subspace. So when we talk about finiteness hypothesis, we have to bear that in mind, that we are talking about not the degrees of freedom within a given theory, which are infinite. And that's, in fact, a welcome feature, because if we believe an extension of the string lamppost principle, that every quantum field theory can be obtained from string theory, that should be realized as objects from perspective of a higher dimensional string theory. So therefore, the finiteness hypothesis does not have any contradiction with ADS CFT correspondence, but it does have a connection, perhaps a weak connection, with ADS conjecture, that you cannot have infinitely many, you cannot have a decoupled scale between the compactification and ADS. So ADS scale is the same as the compactification scale. But by and large, it's kind of a standalone other than that. Now, here I have talked about interconnection between these ideas. Now we have to be a bit more organized and try to see the connections. Some of these connections were two-way streets, and some of them are one-way streets. So one implies the other. So let me actually change these arrows to that, so that to show the directionality. So here I have, for example, shown the directionality of which implies what. Some of them are two-way still, and I have weakened some of the connections which are weaker. I have talked about it with a thinner line, kind of. So you see some kind of a semblance of order here. In particular, there are two sides to these Swampland conjectures. Excuse me. The ones on the right here and the ones on the left here. The ones on the right here are kind of can be captured. Let me just have like this. These four are kind of related. In fact, the combination of cobordism and baby universe conjectures, which are kind of related, give you all the rest. So in some sense, these are kind of subsumed by those. But the other ones on the left here are kind of related, and they're kind of reinforce one another, but none of them really actually is a central role. It seems like they're related in some way. Some of them have bigger roles, like distance conjecture or weak gravity seem to play a prominent role. And then there are some of them which actually are very interesting for phenomenology, like potentially the Transplanckian conjecture or the Dister conjecture. And this finiteness is a kind of a standalone kind of an entity which you don't have a good explanation for. So we can kind of try to unify these kind of picture together by basically taking the right-hand side, this side which had no global symmetries, completeness of spectrum, and all that, as basically unified into the bigger picture of the cobordism classes being trivial, or the baby universe hypothesis, as capturing it. And it's still loosely connected with these other ideas, for example, relations that we had before, but these other relations are kind of there and somehow staying there in some form, which we have not been able to distill into one principle or one connected whole idea. I try to explain they are really related, but we don't have a overarching idea. Some of them are better connected to black hole principles and gravity principles like weak gravity conjecture. Some of them, like duality conjecture, is less connected to principles of quantum gravity that we understand. We have seen that there are dualities, but we don't understand why. So some of them we haven't had a deep understanding. So it would be great if we can try to find more universal features which kind of unify into one basic or one or two basic ideas here, and to try to say what have we learned or what are we learning about quantum gravity. And that's, of course, the aim of the Swampland program, is to find the universality criteria for what constitutes a good quantum theory of gravity. So let me then describe my conclusion, the Swampland ideas are beginning to be sharpened and extended and better understood, there are a number of unifying themes that are emerging, and the web of connection between Swampland criteria is encouraging. Sometimes one of them sounds like, where do you get this kind of criteria from other than some examples in string theory? But then yet that same thing arises in a different context and they are related. So any of such links reinforces our belief in their validity and brings further evidence to their validity. But it would be still, we still miss the basic understanding of why for some of these basic criteria, and we should aim for, obviously, understanding why these are true based on some basic principles like unitarity, or some things that are like anomaly freedom and so on that are much more obvious in some form. And we still don't have such a deep understanding of many of these criteria, and we really have to try to work harder. And hopefully these criteria that we are getting suggest some kind of a better picture, a better idea of how we go about trying to connect various pictures together in some unified fashion. Now here I want to point out that what we have seen here, let me just go back here, the two-sidedness here, this yellow picture and these colorful ones, these yellow ones are kind of kinematical kind of statements, vanishing of some classes and this and that, which smell like kinematic conditions. And the left ones are more dynamical like conditions, which have some kind of inequalities in them. So typically these are equalities, these are inequalities on this side. And the inequalities are typically they have more tooth to bite, they have more implications, and of course, they're more heuristic for similar reason. They are much more powerful, also much less evidence for this side than the right side. There are various amounts of differing evidence for various one of these conditions, but nevertheless, they are there. And so I would like to say that there's somehow, the right-hand side is like the kinematic side of the Swampland program, and they are better understood in a form, and they are unified into the cobordism conjecture. And then there's this dynamical part, which quantifies some of the Swampland criteria, is more complicated and perhaps more interesting. So I'll stop here a little ahead of my time, and I welcome questions. Thank you.
Okay. So let's thank Cumrun Vafa for his nice lecture.
Thank you.
Any questions? We have a lot of time.
Yeah, thank you. Can I ask a question?
Yeah, sure.
So yeah, thank you very much. It was a very nice overview talk, and you showed how everything tied together. So my question is more specifically about the sitter and related to that, and how do you see our universe kind of fit in? I mean, I know there's quintessence, but it also has its caveats, and I mean, string theory usually has 100 or 1,000 moduli, right? And it seems we know how to stabilize a substantial fraction of them. It just, once we want to stabilize every single one of them in the sitter, that things become complicated. I mean, I'm just wondering, do you see quintessence as a solution for dark energy? Do you think most string moduli are stabilized, or are most of them rolling? Are we at the border of the moduli space, or where do we sit? Or
Yes, thanks for the question. So, I mean, from the perspective of the Swampland criteria, the two things that relate to this is the de Sitter conjecture or the Transplanckian censorship conjecture. My personal belief is that we have more evidence for the Transplanckian censorship. The Transplanckian censorship conjecture does allow de Sitter, but the difference between this and the regular de Sitter that people construct in string theory is that it's short-lived. So in other words, you do have de Sitter, but not long-lived de Sitter. So indeed, if you take the perspective of the Transplanckian censorship conjecture, you find that there are these membranes which nucleate the decay for the de Sitter, like Coleman-DeLuca bubbles, and you find effective quintessence again. So even if you had a de Sitter-like situation, it would be so fastly decaying that effectively you are dealing with a situation which is like quintessence. But the difference between the Transplanckian one and the de Sitter is that the slope for this effective potential could be much smaller than the one that you get in the de Sitter conjecture. So in other words, there could be a very shallow slope, for instance, but not zero still. So for example, no eternal inflation type things is ruled out in this trans-Planckian censorship conjecture. You can show that that criteria cannot happen. So this TCC is a more relaxed version of the de Sitter conjecture. It allows you things that are more like having a slowly rolling potential, but sufficiently rolled that would be potentially what we have in our universe. It will also explain part of the coincidence problem, because it turns out that even if you have a de Sitter space, which trans-Planckian censorship allows, it will be so short-lived, which will be consistent with why we are entering an era where the dark energy is just being observed. It's not an accident. It marks the end of our universe according to this decay process of the Coleman de Lucha bubbles. So that is the kind of a picture that suggests. So if I were to bet, I would bet the quintessence / either effective quintessence or quintessence coming from the trans-Planckian censorship conjecture. It sounds to me the more natural path.
Okay. Thank you.
Thank you.
Okay.
May
So
I?
next person, Natis. Yeah,
Yeah.
please.
I have a comment, more philosophical comment, and a question. So I'll start with the philosophical comment, and then you can comment whether you accept it or not. Many people expect that in the context of string theory, there will not be a distinction between kinematics and dynamics. Because if the theory is unique, there shouldn't be such a distinction. So I'm kind of baffled by your separation between kinematic and more dynamical conjectures.
Well,
the second, let me ask both, and then I'll shut up.
Yeah, let me answer to that one, and then we can answer the second one. So here, I'm just saying that it looks like they are different. I'm calling kinematic and dynamic, and they could, for example, be unified into one principle. I'm hoping you're right. So I don't differ with your hope. I don't know if we have evidence or not, but I certainly share your hope. But as a matter of practical fact, these look different. I mean, the right-hand side of this conjecture looks like vanishing statement views look like inequality. Whether they could be packaged into a bigger kinematical type restriction, I would love to see that, but we don't have it yet. So so in other words, philosophically we agree, but whether that happens or not, I don't know.
So the second is a question kind of, I'm a great fan of the website 538, and I see the odds for various scenarios. Can you put a number on any one of these blobs to what odds you would give it?
Well, I once said, Nati, I don't know if you believe it or not, I put 0 odds that any principle of physics we know today is correct.
Really? You think Newton's laws are wrong?
Absolutely. I think all are at best approximations. So I don't believe any of the things we know, we believe, cherished today as principles of physics will hold. We are understanding it better and better. It's not like a math theorem.
This is not an answer to my question.
This is my belief. You asked my statement is that there are different ones. Of course, we have more or less evidence for some of these criteria, as I mentioned. And I rather not put a number next to them, but some of them have more and some of them have less. Because we have more examples, they're more connected to black hole principles and this and that. So we have more understanding. For example, no global symmetries is a very simple idea, and it has connected to black holes and many different things and many different ideas. So you could say there's a lot of evidence we believe in it. So that's one answer to that question. But trying to quantify them or not, one can go over the list of what we have. I cannot associate the number to them really, but I mean, it's clear from the examples and the arguments for them how much evidence we have for each one. But ultimately, I believe or I hope that they will be connected together into one whole. Clearly, it's not satisfactory to have all these different ideas floating around. And the hope of the whole program is to kind of come up with basic things that distill what it is that we are after. What makes quantum gravity? And this is basically the hope here, that to try to find these principles that will answer that question.
Okay.
Hi, thanks a lot, Cumrun, for the nice talk, nice overview.
Thank you.
I just wanted to come back briefly to the cobordism conjecture, since you just mentioned very briefly that it may mean that so any compactification is related and any compactification would admit a bubble of nothing. So my question is simply, does it mean that any compactification is unstable due to this bubble of nothing? Or
No, it doesn't mean that.
Yeah.
It doesn't mean that. It just means that it allows a bubble of nothing. It just doesn't mean it's stable. These are non-supersymmetric configuration. You might have to give high energies to get there. So they might be behind horizons on this and that. So for example, type 2b in 10 dimensions is perfectly nice and stable object, but we expect it to have a non-supersymmetric boundary, admit a non-supersymmetric bubble of nothing. These will be excitations within that theory. So it doesn't not destabilize them.
I see. Thanks.
So that's why I usually don't want to call it bubble of nothing, because the history of bubble of nothing is actually an instability mode. But here, all I meant is that really a bubble of nothing, not in terms of dynamics, really. It's just kinematically it's allowed, not that it would prefer that or anything like that. Thanks for the question, though.
So I have a question, Cumrun. In your original paper on the cobordism conjecture, your argument for why there should be no cobordisms was that such a thing would lead to a global symmetry. And so the way that paper was phrased, it made it sound like no global symmetries, in fact, was implying the cobordism conjecture. But looking at this web right now, it seems that you're saying the opposite. Can you explain why?
No global symmetries does not imply cobordism conjecture. No global symmetry is compatible with this, motivates it. Motivation is not the same as a statement. Cobordism conjecture is much stronger than no global symmetries.
What's an example of a cobordism that would not give rise to a global symmetry?
No global symmetries does not tell you cannot have, for example, a bubble of nothing. Cobordism tells you. Cobordism conjecture tells you should always have a bubble of nothing in a quantum theory of gravity. There's no way I can see that coming from no global symmetries.
Thanks.
Yep.
Any other question? Okay, if not, let's thank Cumrun Vafa for his nice talk.
Thank you. Thanks.
The next speaker is Liam McAllister, and he'll talk about Vacua with small flux superpotential. Yeah.
Liam, you're muted.
You're muted.
I think I'm unmuted now, is that right?
Yeah, that's right.
Can you see my slides?
No.
Just a moment. Now?
Hold on. Yes, now we can see it.
All set?
Yes, we can see it now.
Okay, perfect. All right, let me begin by thanking the organizers for giving me the opportunity to speak here. I'll be talking about work with some outstanding collaborators, Mehmet Demirtas, Manki Kim, and Jakob Moritz. Mehmet and Manki are my graduate students, and they're on the market this year, so if you're hiring, please have a look. This talk is about the search for de Sitter space, and as you know, de Sitter is the simplest explanation for the universe that we observe around us. It's the foundation of the concordance model of cosmology. And we have evidence from supernovae, as shown here, and from the cosmic microwave background, and from large-scale structure besides, for two stages of accelerated expansion. An inflationary stage at very early times, and a dark energy stage now. So we ought to ask whether we can find a de Sitter solution in string theory, and check whether string theory is compatible with the concordance cosmology. Now, if you want to look for a de Sitter, it helps to know what you're looking for. So if you're equipped with an artist's conception of what de Sitter looks like, then it's not so difficult to pick him out. And he's there. In this talk, the artist's conception we'll be using is the KKLT scenario. So this is a framework or a way of thinking about how you might put together components in a solution of string theory that give rise to a de Sitter vacuum. And what we'll try to do is put some of those components on firmer footing in solutions of string theory. So I'll first say a few words about our general approach to this class of problems. I'll then set some notation and review the key aspects of the KKLT scenario. And then I'll explain what we've done in the last couple of years on this problem. So we're looking for a de Sitter solution of string theory, and that's going to be difficult. De Sitter is necessarily non-supersymmetric. And I'm going to go out on a limb and say, I think that an exact non-supersymmetric solution of a superstring theory with four-dimensional dynamical gravity is out of reach for 21st century theorists. I don't think we have the capabilities right now to envision how we would get exact and semi-realistic solutions that are non-supersymmetric. Now, this is in no way a cosmological problem. It just has to do with the breaking of supersymmetry. As Cumrun said, we understand a lot more about supersymmetric solutions than non-supersymmetric ones. In fact, we don't have a derivation of the standard model plus Einstein gravity that's exact, nor even do we have a derivation of the standard model plus Einstein gravity without light moduli in the dark sector to the standard that we're going to be demanding for de Sitter solutions. So we really need to adjust our expectations a little bit while trying to find non-SUSY solutions. Now, non-supersymmetric compactifications are definitely difficult, but that alone doesn't mean that they don't exist. And if we don't have the capacity right now to achieve exact solutions, we somehow need systematic approximations. So the fundamental expansions, as we know, are in alpha prime and G string. And so let's see how we would try to use those to arrive at approximate solutions. A naive strategy you might try, one that's conceptually easy, but turns out not to be very feasible, is first, let's try and find a solution of string theory that preserves n equals 1 supersymmetry in 4 dimensions. For example, compactify type 2 string theory on an orientifold of a Calabi-Yau threefold. And then just directly compute the 4-dimensional effective field theory to some order, k orders beyond leading order in both expansions. Having done that, look at that EFT and check, and perhaps you'll find de Sitter solutions. So these will be solutions that spontaneously break supersymmetry. And suppose you can exhibit them at n to the k-1 LO, then you can just check and see whether the n to the k LO terms, which by assumption we've already computed, are in fact negligible. If you can do that, you would have shown not a mathematical proof, but a proof by the usual standards of physicists that there are de Sitter solutions in that theory. The reason that this is difficult is right now, as a community, we're not particularly good at computing in alpha prime and G string to high powers beyond leading order. That's just not in our toolkit right now. And so as a practical matter, we have all been forced to apply further approximations of various kinds. The most common such approximation is to find parameter regimes in which different sectors of the theory decouple into what you might think of as modules that interact weakly. And then you can study those modules in isolation. Once you've understood them individually, you can try to couple them back together. Hopefully, they'll be weakly coupled. But the final assembly of those modules is a key challenge that cannot be overlooked. It's not enough just to find and understand the individual components or modules. You have to understand whether they can be consistently glued together in a bona fide solution. So our strategy for this general class of problems is to work under the brightest lamppost, which right now appears to be Calabi-Yau compactifications. And our aim is to systematically compute the topological and geometric data. For example, the triple intersection numbers of a threefold, the Gopokumara-Vafa invariants, etc., that enter the 4-dimensional n equals 1 effective field theory. And our aim is to do this for a vast ensemble of Calabi-Yau threefold hypersurfaces in toric varieties. So instead of looking under one lamppost, we'll try to look under an immense array of lampposts and see what we can find. What we aspire to do there is to construct a landscape of Vacua with n equals 1 supersymmetry and eventually with n equals 0 supersymmetry, with eventually, again, this is aspirational, demonstrable control of the G string and alpha prime corrections. I'll be reporting progress in this direction today, but as you'll see, there's a large piece of work ahead. Now, this landscape I'm talking about is the landscape whose statistics have already been well modeled, we think, by Ashok, Denef, and Douglas. But by enumerating Vacua on a massive scale, we can check what actually exists. And to connect this to Cumrun's beautiful summary of the Swampland program, there are some places where the boundary between the landscape and the swampland is determined by a finite set of integers of modest size. For example, the topological data of a Calabi-Yau threefold. These integers determine, in particular, the kinds of undetermined constants that showed up in some of the swampland conjectures. And so why don't we go forth and compute them and actually find out in some places where the boundary between landscape and swampland lies. Now, by following this program in time, we may reveal families of controlled de Sitter vacua, or we may not. So let's see. So that was the aim. Practically speaking, one of our main tools is computational. With my students Mehmet Demirtas and Andres Reyes-Toscon, we've built a code CY tools that can analyze any Calabi-Yau geometry associated with the Kreutzer-Skarka list of hypersurfaces and toric varieties, and can do so orders of magnitude faster than publicly available codes like Sage. In this way, we're automating the search for vacua. So let me say just a couple of words about that. And before that, just remark that all the results I'll actually be showing you today are analytic, although their discovery was computer assisted. So by way of context for the computational progress, this is a plot of the Hodge numbers H21 versus H11 of Calabi-Yau threefold hypersurfaces in toric varieties. And the complexity of the computation grows exponentially as H11 increases. It's not that surprising that higher dimensional moduli spaces are harder to handle. And a massive effort of pioneering work in 2014 by Altman and company managed to study the geometries that fall just in that purple band all the way at the left, the simplest subset of them. And that took 100,000 hours on a supercomputer. But most of the complexity of the problem and a lot of the vacua, we think, are lying all the way out to the right, where H11 is 491. In any case, most of the interesting phenomena, I believe, occur at very large H11, even if not necessarily at that rightmost endpoint. That seemed infeasible, but we rewrote everything from the ground up, rather my students did so. And now we can do in milliseconds things that about 5 years ago didn't seem possible at all. With our code CY tools, we can now analyze anywhere in this realm. So as just a picture of the kinds of things that you can look at once you've acquired this capability, here's a slice, a two-dimensional slice through the Kähler cone in that geometry with H11 equals 491. Each of the individual polygons in here is a region corresponding to a particular triangulation of the associated polytope. Okay, so we can study at a large scale in these complicated cases, and as we'll see soon, high dimension moduli spaces actually do matter. We're going to need to look in such spaces. Okay, so that's enough for sort of strategy. Now let's turn to the KKLT scenario itself. KKLT proposed to consider a compactification of type 2B string theory on an orientifold of a Calabi-Yau threefold. And they said, suppose this threefold includes the following things: a quantized three-form flux, an n equals 1 pure super Yang-Mills sector on a collection of D7 branes, and a warp deformed conifold region, a Klebanov-Strassler throat region, that contains one or more anti-D3 branes. Then they claimed that if you can find all of these modules at once in a solution of string theory, then in a suitable parameter regime, they lead to a metastable de Sitter vacuum, and the corrections to the approximations made are small. So in a little bit more detail about the setup, before we come to asking which of these things we can actually achieve, we're going to study an 0307 orientifold of a Calabi-Yau threefold. So for completeness, here's the line element. The thing I'd like to draw your attention to is that there's a breathing mode e to the 2u of x. X is the coordinate on the non-compact spacetime, and a warp factor, capital A of y, with y the coordinate on the internal space. For simplicity of presentation, I'll imagine there's only one orientifold even Kähler modulus, and I'll use sigma to represent the generator of that unique class in H lower 4 of x, z. And suppose we've chosen some quantized three-form fluxes. Then the moduli of this theory are the axiodilaton, H21 complex structure moduli, UA, which will be the key players in the remainder of this talk. And here, by assumption, a single Kähler modulus, T, which is related to the breathing mode. The associated four-dimensional n=1 supergravity has the following data. There's a flux superpotential derived by Vacua, Vafa, and Witten, given by the integral of the 3-form flux against the 3-0 form omega. And all of this taken over the whole threefold. And then there's some Kähler potential, which we won't work with in great detail. Now, the key point so far is that if you choose generic 3-form flux, so to choose generic quantized F3 and H3, then the solutions of the F flatness conditions for the axiodilaton tau and for the complex structure moduli UA are isolated solutions. That means that the axiodilaton and the complex structure moduli are generically fixed. You could then go below the scale of the masses that those fields have acquired, and the only field left is the Kähler modulus. So we have a single modulus theory. And because the complex structure moduli have acquired VEVs, the flux superpotential also can be evaluated on those VEVs, and we call the flux superpotential evaluated there W0. So that's the main object we're going to want to compute, the VEV of the flux superpotential. Now, in this theory, suppose that there's a stack of D7 branes wrapping the basic divisor sigma, and suppose those D7 branes support SUNC super Yang Mills. Or Euclidean D3 branes there would give a comparable story, but let me not include that now. Then at low energies, this theory generates a gaugino condensate superpotential, which is proportional to e to the minus t, the Kähler modulus. And so the total superpotential is the sum of a flux term and a non-perturbative term. And this supergravity theory, the one written here with this Kähler potential and this superpotential, has a supersymmetric ADS4 minimum. So I've pictured the potential here, and you can easily solve for the F flatness condition for T, and you find that the solution occurs where W0 is given by e to the minus t times the power walk term. If W0 is small in string units, this is the crucial point. If it's small in string units, then the minimum is at large volume. The Kähler modulus at the minimum is proportional to the logarithm of 1 over W0. And that's what's going to allow control of the sigma model expansion. Now, there was a statistical argument that W0 small compared to 1 is not generic. Well, it's clearly not generic, but that it should occur for some of the exponentially many choices of 3-form flux. Here, B3 is the third Betti number of the threefold. I won't give a precise version of this famous statistical argument here because I won't be using it. But this is the context. It was long thought that the way one should argue for this, or the best one could do to argue for this whole scenario, was to say, well, generically small W0 can be found. Not to say that a generic choice of fluxes will give small W0, but there should exist some special choices of fluxes for which the flux superpotential is small. One more thing I have to explain, which is the uplifting to break supersymmetry. I'll be relatively brief here because I won't be saying much later in this talk about it, but we need to know a little bit. So if I further introduce some number P of anti-D3 branes at the tip of a Klebanov-Strassler throat, then the potential that those branes give rise to is proportional to their warped tension, so e to the 4a times the tension. And in a non-compact throat, Khatri, Pearson, and Verlinde argued this gives rise to a metastable supersymmetry breaking state. Once we make gravity dynamical and attach the throat to a compact bulk, the anti-D3 branes also affect the equation of motion for the Kähler modulus. You can see that from the fact that the potential pictured above has an e to the minus 8u. So that means that the potential can be reduced by scaling up the Kähler modulus. Moreover, the anti-D3 branes can in principle also affect the supersymmetric gauge theory on the D7 branes, and so affect the development of a condensate. To the extent that the anti-branes only affect the condensate by contributing to the equation of motion for the Kähler modulus, and this is something that one can quantify, it follows that the total potential is the sum of the F-term potential for the supersymmetric theory I just described, plus the anti-brane potential written here. And in that case, the resulting theory has a de Sitter minimum that's metastable. And in a suitable parameter range, it's long-lived. So this is the scenario, and we should ask a lot of things about it. With regard to moduli stabilization, we ought to ask, do there exist consistent global models, consistent solutions of string theory with the following things? First of all, quantized flux is giving a small classical flux superpotential W0. And at the same time, a warped conifold region, a Klebanov-Strassler through. And at the same time, a suitable D7 brane gaugino condensate, or more than one in the case that there's more than one Kähler modulus. We should also ask about supersymmetry breaking. We should ask, can these de Sitter solutions be described consistently in 10-dimensional supergravity at all? Is decompactification the primary instability coming from anti-D3 branes, or are there other problematic instabilities coming from anti-D3 branes? There are many more questions, but these are the primary ones for now. Putting them all together, you should ask, can you exhibit an explicit and fully controlled compactification that unites all of these ingredients at once? So the answer to the first question is yes, as we've shown recently, and I'll explain that today. To the second question, also yes. I'm going to defer the third question, for which there's been not a lot of very recent progress. To the question of 10-dimensional description, the answer is also yes, following a collection of developments in recent years. Regarding decompactification versus other instabilities from anti-D3 branes, I'm going to be more guarded in my statements here just because I haven't personally contributed to any of the recent developments. But it seems to me from reading the literature that the answer is yes. The dominant problem is the one already envisaged by Khatri, Persson, and Verlinde. But this is not a main point of this talk, although it's worth discussion at some other time. And to the last point, an explicit and fully controlled solution unifying everything, well, that's the hard question. That's very much to be determined, and I certainly won't resolve it today. What I will do is these first 2 points. All of this occurs at the level of the classical theory. And it's once you cross over to quantum effects in item 3, D7 brane gaugino condensates, that things start to get much more complex. So why do we need a small flux superpotential? As I've shown you already, the value of the Kähler modulus at the minimum is proportional to the logarithm of W0. So control just requires that W0 is small. The statistical arguments that suggest that W0 should occur say that it should occur exponentially rarely and preferentially when the moduli space dimension is large. So that's sounding pretty bad because analyzing such moduli spaces will be tough. In fact, with the tools that we've developed, we can explore in such spaces, but a brute force search is still going to be extremely challenging. And in fact, the previous record in sort of a well-studied model is of order 10 to the minus 2. So that's the smallest value of W0 previously achieved. It's better to invent and apply a mechanism. We'll be following a mechanism proposed by Girievets and company and by Denef and company some years ago, which we've added a few twists to and made to work on a large scale. So what mechanism? Well, now we come to the artist's conception of the mechanism. We're going to consider a racetrack superpotential. So first at the sketch level, what's a racetrack superpotential? And then we'll turn to actually getting it in string theory. Suppose I have an n equals 1 supersymmetric theory of some field U. And let's say that the superpotential for U is split into a perturbative piece and a non-perturbative piece. And I'll choose normalizations, et cetera, where the non-perturbative piece involves exponentials like this. So U goes to I infinity is the regime in which the instantonic terms are heavily suppressed. So that's the analog of the weak coupling regime. So here A1 and A2 are some prefactors, and P1 and P2 are going to be rational numbers. Now, suppose that in this theory, this toy theory, we want to minimize the potential for U at some place U min. And we want to do it at a place such that when you evaluate the superpotential at U min, it's small. So can we minimize U where the superpotential is small? Well, let's further suppose that in this theory, we can find a region, let's call it U flat, that's a region in the field space where the F terms for the perturbative superpotential and the perturbative superpotential itself vanish identically. I'll call that a flat direction. By no means does every theory have this property, but suppose that we find a theory with the property that there's a flat direction. And along the flat direction, the perturbative superpotential and the F terms from the perturbative superpotential are identically 0. Well, in that case, the effective superpotential along the flat direction is just the instantonic one. And the instantonic one is a sum of two exponentials. In this case, the minimum of the potential we can look for along the flat direction, and it'll be determined by the F flatness condition from the instantonic superpotential. Well, the F flatness condition for the instantonic superpotential is easy to read off from this superpotential. If we ignore Kähler covariantization for a minute, one can check in detail in the examples. I'll show that that isn't a big effect. Right, just write down the F terms for W inst, and you find that the minimum value u min is at some place given by this expression. So some log of some ratio of constants over P1 minus P2. Plug that thing back in and evaluate the instanton superpotential, and you find that it's equal to, well, some ratio to some power. And if the term in the round parentheses is small and the exponent is big, then W inst at U min is exponentially small. Okay, so this is the racetrack mechanism. It's an ancient idea, and we're going to make use of it. Now, for this to do us any good, we actually have to show that in a bona fide solution of string theory, first of all, the flux superpotential, that's the superpotential we're going to study, does split into a perturbative and an instantonic piece, with the instantonic piece looking something like this, and with a flat direction, which is not guaranteed at all, and with the particular property that it really makes a racetrack, that P1 minus P2 is small compared to P2, and that the prefactors are hierarchical. So conditions 2 and 3 are not guaranteed by any means in general. If we can do that, though, we will have succeeded, because then W naught, which is the VEV of the flux superpotential, will equal the instantonic superpotential at the minimum. And that will be given by this simple expression, which, when condition 3 holds, is exponentially small. So we'll have an exponentially small classical flux superpotential. Now, point 1 is actually immediate. If we're working in a type 2b compactification, then type 2a worldsheet instantons in the mirror do give rise to exponential corrections of this form. So no problem for item 1. For item 2, we established a sufficient condition on the topological beta and showed that this can sometimes be fulfilled. And for item 3, we just found explicit examples. I'll show you one now. Okay, so what we're talking about in the remainder is just an incarnation in string theory of the racetrack idea. Okay, so concretely, suppose X is a Calabi-Yau threefold, and I have a symplectic basis for the 3 cycles. Then I can define the periods to be the integrals of the holomorphic 3 form over the B cycles and the A cycles. The integrals over the A cycles I can use as my local coordinates, the complex structure moduli. And the integrals of omega over the B cycles are the derivatives of the prepotential F with respect to those moduli. So we'll write the prepotential as a perturbative plus an instantonic piece, and we'll work around large complex structure. Then specifically, the perturbative prepotential looks like this. It's cubic. It has a term coming from the triple intersection numbers and 2 other terms involving some constant objects A, AB, and BA, which we'll come to momentarily. But you should just think of them as numerical for the moment. Now, the instantonic term, I'll write it in a schematic way now and be more detailed shortly. It involves a sum over some charge vectors Q of some prefactors times some exponentials. Then from these data, we can derive the superpotential, and the flux superpotential involves the vector of 3-form fluxes F minus tau H contracted with the period vector using this symplectic form sigma. And just as the prepotential splits into a perturbative and an instantonic piece, so too does the flux superpotential split into a perturbative and an instantonic piece. Now, these data here are all computable, rational data. So let's compute them. To compute them, we have to, of course, be specific about which geometry we're looking at. So let's let X tilde be the famous Calabi-Yau threefold hypersurface in weighted projective space with weights 1, 1, 1, 6, 9. This is a threefold that has H11 equals 2 and H21 equals 272. Now the mirror of this space is the resolution of x tilde mod the green Plessur group C6 times C18. And the mirror, of course, has the reverse Hodge numbers. It has H21 equals 2 and H11 equals 272. And X is the space we'll study today. So we wanted the perturbative prepotential that had these data highlighted in blue, and we can just work them out. The perturbative data are given by these values. So here they are, just some rational numbers. And we wanted the instantonic terms, and these we have from olden times. Note that in the expression given here, there are sizable hierarchies in some of the numbers. So among the one instanton terms, Q1 and Q2 are two different one instanton terms, and there's a hierarchy between the two, right? Coefficient 540 in terms of one and 3 in front of another. Okay, so this is just what it is. This is how the prepotential looks in this particular geometry. What we're going to do is take this is an n equals 2 compactification so far. We're going to find an O307 orientifold of it and a choice of quantized fluxes. So just to be very specific, here are the fluxes. The vector f and the vector h are given in terms of some more basic integer data. And the point of this is just to show you these are nice, reasonable integers of modest size. So there are some fluxes. And it turns out the D3 brane charge tadpole for that collection of fluxes is 124, which is fine in this geometry. And it turns out, we show that with that choice of fluxes, there is a flat direction. So there are two complex structure moduli. Remember, H21 is equal to 2. And there's also the axiodilaton. And in that three-dimensional space, there's one flat direction in which the complex structure moduli are proportional to the axiodilaton. And the proportionality vector has entries 4/10, 3/10, as shown here. Okay, so we've exhibited a flat direction. And along the flat direction, we can evaluate the instantonic superpotential. And it looks like this, as shown in red, with the exponents being 2/5 and 3/10. And the ratio of the prefactors is a small number. So these are all the things that we wanted. When we substitute these data, we find that the moduli are stabilized. Such that tau is equal to about 7 times I, and W naught is 10 to the minus 8. Sorry, I think the bottom of my screen is hard to see here. That says that W naught is 10 to the minus 8. So great, this is an example of an exponentially small flux superpotential in just one geometry. Some things to note about it. The single instantons dominate, as I'll show in a moment. And all of it is totally explicit. There are no unknown factors in this leading order data. There are no order 1 estimates of things, just a finite set of computable rational numbers, and we computed them. And so it's all clean and tidy. The higher order terms are strongly suppressed. So we made use of the things listed in blue. Those are the leading instantons. And the next order terms written in red are a factor 10 to the minus 5 smaller. The next order terms written in green are a factor of 10 to the minus 10 smaller, et cetera. So we have very good control of the instanton expansion here. One general remark, an observation about this vacuum, is that the mass squared along the previously flat direction, remember there was a flat direction, is of order W naught. So it's comparatively small. And when we eventually study the masses for the Kähler moduli, those will be of the same order. So there's actually going to be 3 light fields in this theory that will need to be stabilized. 273, 272 Kähler moduli and 1 flat direction in the complex structure moduli space. However, although this mass is small compared to the string scale, it's not 0. The Hessian for the complex structure moduli and axiodilaton is positive definite here. Now, a general comment is based on the computational tools that I was describing previously. We can easily find many more examples. I've just shown you one here. What do you need to make one work? You need to know the prepotential around large complex structure. You need to find a suitable orientifold. And you need to have a little bit of luck with the numbers, P1, P2, A2, and the D3 brane tadpole. But you only need to have a little bit of luck. A polynomial degree of luck with these numbers leads to an exponentially small flux superpotential. And so we don't have to actually execute a brutal exponentially hard search in order to find exponentially small W naught. The upshot is we've shown that small W naught is in the landscape. But we wanted a lot more than that for a KKLT de Sitter vacuum. We wanted a conifold region, Kähler moduli stabilization. And look, there's 272 Kähler moduli in this example. So that's going to be very hard to stabilize. One can try, but it's going to be hard. And one wants anti-D3 brane supersymmetry breaking. In the remainder, I'll just tell you a little bit about this. The others are work in progress and may turn out to be challenging in various ways. So far, everything I've done has been expanded around large, complex structure, but we really need to find a flux vacuum that's near a conifold point and with W naught that's small. To find a flux compactification that has a Klebanov-Strassler region is a long solved problem. That's quite straightforward in general. You go to a near a conifold point in moduli space and introduce appropriate fluxes. The trouble is you want to do that in such a way that the fluxes that you put in to make the conifold be a warped conifold do not disrupt the smallness of W naught. And that's the work that remains. Now, to achieve that using the methods that we've already built, we're going to need to somehow understand the periods, pre-potential, near the conifold point. And we know them near large complex structure. So what we'd like to do is to analytically continue from large complex structure to the vicinity of the conifold, and then perhaps we'll be able to extend our mechanism to that region. So to be explicit about this, I promised a more detailed formula for the instantonic terms. What I'm showing here is a sum over curve classes C that are effective curves. And let's think of those as being expanded in terms of a basis of H lower 2 with some coefficients B. And then the instantonic prepotential involves a trilogarithm of an exponential of the complex structure moduli. And the prefactors N0C are the genus 0 Gopakumar Vafa invariants. Okay, so this is the object that we would like to analytically continue. And the trouble is the following. If we're going to near a conifold singularity in X, the space that we care about, then we can ask, what's the mirror of that on X tilde? So the mirror of developing a conifold singularity in X can be collapsing all of X tilde, or collapsing one or more divisors in X tilde, or collapsing one or more curves in X tilde. And quite often, one finds that an infinite instanton sum contributes as you approach the conifold. And that's troubling because if you don't know that entire sum, in particular, know all of the GV invariants for that entire list, you're not going to be able to understand what actually happens there in detail. Okay, so that doesn't mean that the configuration doesn't make sense, but it does mean it's going to be very difficult indeed to compute it. But there's a special case. If the conifold singularity happens to be mirror to collapsing some curve, call it C1, such that the genus 0 GV invariance becomes 0 for all curves k times C1 with sufficiently large k. So there's only finitely many multiples of C1 that have non-zero GV invariance. If that's what's mirrored to the conifold singularity, then actually you only end up needing to continue finitely many polylogarithms. And that you can do thanks to almost 300-year-old result due to Euler, the Euler reflection formula. And if you just take that and apply it in the prepotential that I wrote down previously, you can write down an analytic expression for the prepotential near a conifold. And so have a look at this. The first term you see involves a z log z. That's what you would have expected for a conifold. And then there's a whole infinite series of corrections. But if we want to understand those corrections, we can compute them systematically. The sum is over curve classes that are not equal to the collapsed one. And so all of those are well controlled. So we can just compute the associated GV invariance to the desired degree and then get an accurate representation of the prepotential. Having done this, we found an explicit orientifold with H11 equals 99, H21 equals 3. And in that geometry, we exhibited near conifold vacua in which the warp factor, e to the 2a, and W naught are comparable in size and both small compared to 1. That's the hierarchy that you want for an uplift to a de Sitter vacuum in KKLT. So let me conclude. The KKLT scenario for de Sitter vacua requires rather special structures already at the level of classical flux compactifications. It requires an exponentially small flux superpotential W naught. It requires at the same time a warped conifold region. We presented a mechanism for constructing such solutions via a racetrack of type 2A world sheet instantons, and we gave complete and explicit examples at this classical level. So a small W naught is in the landscape. Our search is automated, and so large-scale studies are possible, and we are beginning some. And it should be possible to understand a great deal more about these configurations in the coming years. However, the quantum side of KKLT and the uplift to de Sitter space remain very challenging, at least in this very explicit context. What we have shown, though, to some extent, is that you can take some of the elements of the KKLT scenario that were at the level of an artist's conception and make them more realistic in explicit geometries. Thank you.
Okay, so let's thank Liam for a very nice talk. Any questions?
Hello, I have a question.
Yes, please.
Yeah, I hope my connection is okay. So thanks, Liam. I want to know whether your construction crucially relies on some fine-tuning freedom in the ratio of instanton determinants.
On the ratio of instanton determinants, well, it certainly does. However, the ratio in question is the ratio of instanton determinants that are pure numbers. So here, in this example, the hierarchy that we got crucially involved 3 over 540. Now, I myself am quite queasy about, okay, I have been queasy about racetracks in general n=1 compactifications for some time. Of course, the idea has been around for 30 or 40 years. But the difficulty, in my view, is just saying, here's an EFT that has a racetrack, now this can achieve some previously difficult thing for me. This smells a bit like cheating. And I wouldn't be comfortable personally at this point creating a racetrack, for example, of Euclidean D3 brane contributions in which the Pfaffian prefactors, the things I'm writing curly A here, were just unknown and estimated to be order 1. All the work goes in controlling them. But here, because we actually know the prepotential, I just know what those prefactors are, and they are -540 and -3. And so I think it's totally locked down. It is, however, the case that that hierarchy is required. So this is always the case in a racetrack, right? The smallness comes from the ratio A2P2 over A1P1, then to some power.
Okay, thanks a lot. Yeah.
Any other questions?
Hi, here's David. I have a question, if possible.
Yeah.
Hi, Liam. Yeah, thanks a lot for the nice talk. Given you listed various difficulties with KKLT, I was just curious to know whether you had any opinion or reaction with respect to the recent work by Hebecker and Jungans and the collaborator.
I don't have, let's say, a complete analysis of that work. I'm not convinced that the problem is as general and as complete as what they are stating. I'm comfortable with the claims made in the earlier work of Carter Moritz Westphal, where they were essentially saying, well, there is generically a kind of problem, but really dialing in all of the constants and being sure that this is something very hard to avoid, that's not something that I've understood yet to be true. It could be true, but I don't quite see it. So I think this is something that'll be well worth figuring out, though.
Thank you.
Any other question? If not, let's thank Liam again for his nice talk. The final speaker of this session is David Andriot, and he'll be talking about, do classical de Sitter string backgrounds exist?
Yes. So let me share this.
Yeah. Can you go full screen?
Yes. All right.
Yes. Good.
Is it fine?
Yes, that's fine. Please.
Okay, thank you very much. Thank you very much to the organizers for organizing this this conference. Of course, I would have liked to come to India, but I hope I'll do this another time. Still, it's very good to have such a meeting now. Today I will talk about classical de Sitter string backgrounds, and this is based on various recent work. This review, this paper, which can serve as a review and extension by myself, and some recent work with Niccolò Crebiori and David Erkinger, and more recent work with Paul Marconnet and Tim Brase. All right, so the topic of the day is de Sitter solutions, and by this I mean solutions of some theory which admit a four-dimensional de Sitter spacetime, meaning that the four-dimensional Ricci scalar is given by a cosmological constant lambda, and this is positive. As said several times already in the previous talks, the de Sitter solutions or quasi-de Sitter solutions appear in cosmological models which are in good agreement with observations. They appear in periods of accelerated expansion, where the dark energy is well approximated by cosmological constants. So for instance, our late universe as described by lambda CDM, or the early universe as described by a slow roll single field inflation model. So for this reason, it's a natural question to ask whether de Sitter solutions can appear in a fundamental theory or a theory of quantum gravity. And here we're interested in string theory. And as you know, and has been said already, the answer is that it's actually difficult to get a well-controlled de Sitter solution. So there has been various approaches to this problem, perturbative or not. I think Tim Brase and Thomas van Riet yesterday and Liam McAllister today have presented various approaches, especially non-perturbative like KKLT or the large volume scenario. But here in this talk, I will focus more on the classical regime. And so I'm going to consider classical de Sitter string backgrounds. So what is this exactly, and why do we consider those? Well, the motivation is that the framework is fairly simple and well-defined, and therefore we have good chances to control the approximations that are needed. Okay, so what are we talking about exactly? In practice, we are talking about a 10-dimensional spacetime, which is split as a 4-dimensional de Sitter and a 6-dimensional compact space M. And this typically is not enough, but this goes with fluxes and D-branes and orientifolds. So we are looking for solutions of this kind within a certain theory, so either 10-dimensional description, like a supergravity, or sometimes a 4-dimensional effective description together with a scalar potential V, in which case the solution is an extremum of the potential. So in such a framework, the question is very clear. Do we have de Sitter solutions or classical de Sitter solutions? This is a fairly well-posed question. I can give you an explicit list of equations to be solved and constraints to be solved. And so we can try to address this question. So what is the answer? Well, there's actually a cost to simplicity. Indeed, in this framework, we do not have many ingredients at hand, and therefore it's a very constrained framework. There are many no-go theorems, and it's very difficult to find such solutions. Actually, no classical de Sitter string background is known up to date, but this possibility is not yet excluded. This brings me back to the initial question, do classical de Sitter string backgrounds exist? And so together in the first part of this talk, we're going to go through some attempts to find these solutions and maybe also to find some more constraints. However, we've seen early on today with the talk of Cumrun and Vafa that there is another approach through the Swampland program. So there's been a conjectured answer to the previous question, which is no. So this takes place in the Swampland program, which aims at characterizing what can be obtained from string theory. So one specific question in this program is, can one obtain de Sitter solutions? And the conjectured answer is that no, it's not possible, at least in some asymptotic regime, which may correspond to a classical regime. So well, these are conjectures. So the question is, can we actually trust these Swampland de Sitter conjectures? And the thing we're going to do now is to actually try to test these conjectures as accurately as possible. And we'll actually manage to test them quite accurately by comparing them to no-go theorems. So I will present this in the second part of the talk. Well, if this is really true, one may wonder whether there's a deeper physical reason for the absence of classical de Sitter backgrounds. And maybe we can see this reason through the various relations between the Swampland conjectures, the web of conjectures that was summarized by Cumrun Vafa in his talk. And maybe then this will hint at a more fundamental principle behind this obstruction. So I will only say a few words in the end on this idea. So the plan of my talk is first to search for classical de Sitter string backgrounds and discuss the difficulties that are faced. Then I will turn to the Swampland de Sitter conjectures and the no-go theorems, and we'll see that there's actually a very surprising and quantitative match between the two. And finally, in the last minute, I'll say a few words about going deeper into the web and the relation of this question to the Swampland distance conjecture and possible bounds that we can then propose. All right. So before I move on, let me give this list of more recent references compared to my papers. And this list is certainly incomplete, and I apologize for those that I missed. And I also apologize to the authors here because I will not have time to discuss all these developments, but it's also to say that the topic is very active, and that's quite an exciting topic now. Okay, so classical de Sitter solutions. So we are looking for solutions of 10D supergravity, which again have this space-time, a 4-dimensional de Sitter space-time and a 6D compact manifold. And typically this goes with fluxes and intersecting orientifolds and D-brane sources. And typically the 6D compact manifold has some curvature. The 6-dimensional Ricci scalar R6 is typically negative. At least this is the typical ansatz I'm going to consider, where the 6-dimensional compact manifold is a group manifold, and we assume that the fluxes are constant, and we take the sources to be so-called smeared. This ansatz is standard and has many advantages, but let me say that it's a different ansatz than the one considered more recently in this series of papers, and I will not consider that ansatz any further in the talk. So in this framework, if you want to find classical de Sitter string backgrounds, there are two steps. The first step is to find solutions of 10D type 2 supergravity, which exhibit de Sitter. And as I've just said before, this is a very constrained problem. There are many no-go theorems. Despite this, you can still find some solutions of this kind. And the solutions found have been found in this list of papers. Typically, these solutions have been found in type 2A with intersecting O66, or some sort of T-dual version of this with O5 and O7. And later on here in the talk, I will present new solutions that we found with O5D5. Okay, so this is the first step. And the second step is to verify that this supergravity solution is indeed part of a classical string regime, meaning that you need a small string coupling GS, a large volume, and this sort of requirements. I'm going to give these requirements more precisely later. And this topic has been discussed in this series of papers from various angles. And it turns out in the end that none of the solutions found as a supergravity solution survive this second check. So there's no solution left at the end of this. And well, up to date, it's not completely clear why and whether this should be true in general. Okay, so let me start with the first step now. So we're looking for supergravity solutions. So to do this, we need to know a bit about the no-go theorems and the parameter space. So it turns out that if you combine only 5 supergravity equations of motions and Bianchi identities, you can get quite a lot of constraints already. So I I will show this table a couple of times, and this represents for me the parameter space and the various possibilities. So the sitter solution requires typically what I call T10 to be positive, where T10 is the source contribution. Essentially, it means this being positive means that you need orientifals. So that's the first requirement. And given this, you need you can have various options. Either you have a positive R6 or a negative R6, and you can also vary the P, which is the size of your sources, the orientifals of the D-branes. And so with these various constraints I mentioned, you can get this table where every time there is a cross, it corresponds to a no-go theorem. Means you cannot get a de Sitter solution in that case. And as you can see, there's only a small corner, what I call a small corner of parameter space or a small region, which is left, where it remains possible to find de Sitter solutions. So you read from this that, okay, you need orientifals, you need a negative curvature, you need P equal 4, 5, or 6. You need some, Ramon-Ramon flux, which is non-zero. I haven't written this here, and there are a few more restrictions. Okay, actually, there are a few things that we know in addition. You typically need to have intersecting sources. That means that the orientifals and D-brane typically wrap different directions in your internal space. And the type 2A examples of known solutions certainly verify everything that I've said. They have intersecting O66, they have negative curvature, they have a non-zero Raman's mass. Okay, so this is very constrained because there's only a small region which is left. But the good thing about this is that it also tells you or indicates where to look if you want to find new solutions. You need to look in this corner. And that's what we did in our work. And therefore, we looked for type 2B de Sitter solutions with intersecting O5D5. We had some more insights and some more motivation on how to place our sources because there is actually a strong analogy between some cases with P equal 5 and P equal 6, as noticed in this paper. And for this reason, we decided to place our sources as follows. So we had 3 sets of sources. All the orientifals and D-branes are along the 3 extended space dimensions in the 4D spacetime. And then there are different directions inside the 6D compact space. The first set wraps the first 2, the second set wraps the other 2, and the last set wraps the last 2 directions. So this specific placement of sources is inspired by this analogy. Okay, a last point to be mentioned is that we're looking for solutions on group manifolds, and the geometry of those is actually specified by some underlying Lie algebra. And therefore, most of the geometric data is encoded in some structure constants, FABC. Okay, that's all you need to know. So given this, this whole framework, you now just plug in all the equations and you, well, essentially make the computer run. And you look this way for solutions. That's what we did. And we found numerically 17 new de Sitter solutions in type 2B supergravity with intersecting O5D5 on group manifolds. Why numerically? Well, it's because we have been solving 46 equations depending on 43 variables in that case, and several constraints like the sign of R4. And so even though you could try to tackle this by hand, it remains challenging. So to give you a taste of what a solution looks like, well, a solution is a set of values for these various fluxes and structure constants of the geometry and the source contributions. And the numbers which are given here correspond to one solution in units of 2 pi ls. Here you can see that the 3 source contribution, T10.1, T10.2, T10.3, corresponding to the 3 sets of sources have bias signs. The first 2 are positive. This means they have orientifals. And the last one is negative and has only D-branes. And for this solution, we find a positive Ricci scalar as expected for the sitter. Okay. So this is one example, and once you find such an example, there is some technicality to further check, which is the compactness of the group manifolds. And this is a bit technical, and I don't have time to explain the details here, but essentially because of the way we proceed, we need to identify the manifold we're talking about from the structure constants, and therefore the actual algebra. And then we need to check whether there's a lattice which exists, which allows to make this manifold compact. And this is not always guaranteed, and it's quite difficult to do in general. So we could only prove this for 4 solutions, but for these 4 solutions, we're sure the manifold is compact, and so it's a good solution. Okay, so I have interesting classical de Sitter solutions in supergravity. Before turning to the question of whether they are actually classical string backgrounds, whether they're part of a classical string regime, I will just make a small parenthesis about their stability. So this is interesting because it turns out that all the previously known 10D supergravity de Sitter solutions were found to be perturbatively unstable. This means that from a 4-dimensional perspective, there exists a tachyon, or a maximum of a 4D potential in some direction. There's been many works on trying to understand this or prove this, and I apologize for not giving the references here. Also some related Swampland conjectures. But this property is not, although observed in all examples, is not fully established analytically. So it was interesting to test again the stability here. And not surprisingly, we found they were all unstable. So to show this, we developed some tools, some potential in terms of 4 scalar fields and the related kinetic terms. And this was enough, indeed, to prove that all the 17 solutions were unstable. This is pictured here, where you see there's an extremum of a potential here, which is positive. And you see that in this direction, this is a maximum, so it's a tachyonic direction, but in the other direction, it's clearly stable. Another word on this, we could evaluate that the eta v parameter was smaller or equal to the values here, so -1, -2. Therefore, it's not even good for Schroer single field inflation. But I would like to point out that maybe this is still good for multi-field inflation in models where you allow for non-geodesic motion or strong bending in field space, as developed by this in these papers, for instance. So maybe it would be interesting to check this. And it would also be interesting to use the insight that we gain from these examples to really prove formally the systematic presence of a tachyon. Maybe get a bound on eta v as well. That would be interesting. Okay, so with this, I close this parenthesis on stability, and I come back to my supergravity solutions. Now I ask the question of the classicality or classical regime. So given a supergravity solution, is this a classical string background? Well, to establish this, we determined 5 requirements, which we think are sufficient. They might not be necessary. We might be asking for a little too much. Okay, that's the way we could formulate things at least. Okay, so the first requirement is to have a small GS, and as you know, and also a large volume. So we want to make this a little more precise. So we want GS to be much smaller than 1. And here, to put some numbers in the game, we put a hierarchy of 10. So we ask GS to be smaller than 1/10. I'm just noticing that it's getting a little dark. So let me just turn on the light. That's a little better, maybe. Okay, and for the large volume, we made this a little more precise by requiring that any of the 60 radii, so the 6 radii are A, should be much bigger than 1 in units of LS, of the string length. So again, we took a hierarchy of 10 just to put some numbers, and we ask the radii to be bigger than 10. But this is not enough, because you also need to make sure that the fluxes are quantized, at least the harmonic components of the fluxes. So in our conventions, this means that the fluxes are given by some integer, n, divided by some radii. You also need to take care of the number of orientifolds in each set. Indeed, the number of orientifolds is finite, and this is fixed by the geometry, so you cannot arbitrarily decide on it. what matters is actually the number of sources NSI in each set I, and this is given by the difference of the number of orientifold to the number of d-branes. And so this is bounded by the number of orientifold, which remains finite. This number of sources is the number which enters in our source contributions D10I. And so we need the number of sources to be integer and to be smaller than the number of orientifold, which is bounded. Okay, and last but not least, there are some lattice quantization conditions on group manifolds. Indeed, the structure constants should be given by some numbers NA, which have to satisfy some quantization conditions to be sure that the manifold is compact at least. Okay, so these are 5 requirements, and it's quite tough in general. And it's fair to say that the last 3 conditions actually need a detailed knowledge of the 6D geometry, because they all depend in one way or another on the geometry. And as I very briefly mentioned earlier, because of the way we proceed, we're not always very sure of which group manifold we're dealing with. Therefore, we could not really check this whole list of requirements on all our examples. Actually, we could carry this full program only for 2 solutions. For these 2 solutions, we verified that they cannot be made classical de Sitter string backgrounds. For the other solutions, we could make some partial checks of these requirements, and still these partial checks were successful for 2 of the other solutions. But that's all I can say on those solutions for now. So to give you a concrete taste of this, it's good to look at an example, and that's some numbers. So for the solution 14, we could satisfy the first 4 requirements, but not the 5th one. So you can see that GS could be made small, the radii could be made large, fluxes are quantized, the sources are not too big numbers, but the lattice conditions could not be satisfied. You could actually turn this around and satisfy all the requirements except the orientifold bounds, meaning that then the number of sources was too high. I think this is a problem which is also found sometimes in the KKLT contexts, playing with all these integers and so on. You could also require to satisfy first all the conditions on fluxes, sources, and lattice, and then study what you can do with GS and radii. And again, then you could get a small GS, but not large radii, especially some of them were substringy, which is certainly problematic. Okay, so that's the situation. So, well, there are several comments to be made. First, I think it's fair to say that this analysis is quite complete and detailed, and I think it goes beyond what has been done before in the literature. But this is also thanks to the fact that we have very concrete examples. It's also fair to say that it's almost working. We could satisfy 4 out of the 5 requirements. And so it's not very clear why it's not working, whether it's just bad luck with our solutions or whether it is actually a general property of string theory that it will never work. This is not clear. However, it's clear that it's a very constrained problem, right? There are tons of requirements, tons of bounds of all sorts, either on the number of fluxes, number of sources, etc. And so we try to play a bit with this and to move or deform or rescale our solutions in one direction or another in parameter or moduli space. And every time we would do this, we would actually hit one of its bounds, which needs to be satisfied. So this gave us this idea that classical de Sitter solutions actually live at best in some bounded region of parameter space. They probably do not live in the asymptotics. And this is, in a sense, in agreement with the Swampland conjectures. So we discussed this pretty much at length and explicitly in the paper. So if you're interested, I refer you to the paper. I just made this little picture here to illustrate this. I apologize for the quality, but and the idea is that you have some field space or parameter space or moduli space. And as we know, it has some asymptotic regions like this sometime. And you can imagine that here, when you go towards this asymptotics here on this tip, it's as going as to a large value of this L, which can be viewed as some internal radius or some internal size. And here it's the value is the string length. And so if you go a bit beyond this, you then enter what you could call the classical regime, as we did with a factor of 10, for instance. So this whole region here would be the classical regime. And what we suggest is that classical de Sitter solutions can only be found in some bounded region here. And it cannot be found at the tip here in the asymptotics. Right, so that's the idea. It's not clear if it's true because so far we haven't found any solution in this small bounded region, but that could be the case. This description should be, sorry, let me add something about the Swampland conjecture. So the Swampland conjectures, as we'll see in a second, and as Cumrun Vafa recalled, say that there cannot be any de Sitter in the asymptotics. And therefore the question is, what is here the asymptotics? Is it only the tip, in which case it's consistent with this picture, or is it the whole classical regime? Or in other words, what do we mean actually by classical regime? Yeah, so that's, to me, an open question. This discussion should also be compared to the question of scale separation and classicality for anti-de Sitter solutions, especially, for instance, the DGKT solution, where the two things of scale separation and classical go together. And in that case, indeed, in this picture, you could go all the way to the tip for the anti-de Sitter solution, so to the asymptotics. And it's also true that for anti-de Sitter, you typically do not have all these bounds. For instance, in the DGKT, there is no lattice constraint because the solution is found on a flat torus. Also, sometimes in anti-de Sitter, you don't need orientifold. So there are all these sorts of bounds which drop for anti-de Sitter, which in a way could open up this region and allow you to go all the way to the asymptotics. So that would be the difference between de Sitter and anti-de Sitter. So again, if you're interested in all this discussion, I refer you to our paper. So to summarize what I said so far, I presented you that there are various no-go theorems which indicate a remaining region in parameter space where to look for de Sitter solutions. And if you do so, you can actually find de Sitter supergravity solutions, and that's what we did. And after that, you need to do this classical regime analysis, and that's what I've done here and what I commented on. Okay, so that's it for this question. That's where we stand, essentially. Now I will turn to the Swampland de Sitter conjectures. Okay, so I will be quick on this because I think this has been mentioned several times already. As you know, there's been several conjectures in the Swampland which have been proposed, and both forbid de Sitter solutions or classical de Sitter solutions. And here we want to test them. So let me first recall these conjectures. So the initial version has to do with four-dimensional theory of minimally coupled scalars, phi, coupled to gravity, and there's a scalar potential V. And the criterion for this theory to be in the landscape, meaning to be an effective field theory of string theory, is the following. The potential needs to satisfy this inequality. So the gradient of the potential, which is essentially the first derivative of the potential, should be bigger than the potential itself up to a constant C of order 1. And so this is the criterion to be satisfied for this to be obtainable from string theory. And therefore, this implies that there is no de Sitter solution which can come from string theory because the de Sitter solution would be an extremum of a potential, and therefore the potential would be negative or 0 at this extremum. So that was the initial proposal, and there's been various criticisms about it that Cumrun and Vafa mentioned already. The first question was whether this was just example-based, for instance, based on the no-go theorems, or whether there is a deeper physical reason to propose this. The second question is, what is actually the value of C? What does it mean to be of order 1? And the last criticism maybe was that actually maybe you should allow for maxima, so de Sitter maxima. So all this criticism led to various refinements the first type of refinement was indeed about stability and maxima. And so people proposed to include the second derivative of potential, or the eta v parameter. And I don't really have time to comment on this here. The second sort of refinement, which is a little more subtle at first, is to say that, well, actually what you can say is that there is no de Sitter solution in the asymptotics of moduli space. As I just discussed a minute ago, the question is whether these asymptotics do correspond to classical regime. But that's what you would at first think about. So this refinement is reminiscent, or is a generalization of a Dine-Seiberg argument, and therefore now you should view this inequality as valid in large field distances. Then, very interestingly, there was this Transplanckian censorship conjecture. And the idea there was to propose some physical arguments about Transplanckian modes that I don't want to recall here. I don't have time to recall this, but it's a conjecture, it's a physical conjecture. And when you apply this to the case of a scalar field phi with some potential, you derive then this inequality on the potential. So the potential is bounded by some decreasing exponential with some fixed number C0 here. And from this inequality, you can derive this inequality on the ratio of the first derivative of potential to the potential. There's also here an average and a large field limit. This ratio is then bigger than this number C0, which is equal to square root of 2/3 in 4 dimensions. So this is very interesting because it should be compared to this ratio we had before with the gradient of potential and the C number. And it's interesting because it gives a physical motivation given by this physical argument to get such an inequality. And it also gives a number. So at least that's the way we interpreted this in our paper, that the C should always be bigger than the C0. That's what we call this TCC bound. The C is bigger than the square root of 2/3 in 4D. In that way, it answers the criticisms that were mentioned before. And what is also very nice is that in this proposal, the asymptotic limit is actually crucial. It's only in this limit that you get this inequality. Okay, to be complete, I should also add that there were also some consequences on the second derivative of the potential and the stability that I don't really have time to recall here. Especially there was a bound on the lifetime of a universe which was proposed, and this has been related later on to the scrambling time in de Sitter in both papers. Okay, so but I will not talk on this. All right, so these are the Swampland de Sitter conjectures. And now the idea is to try to test these conjectures as precisely as possible. And we will do so with the no-go theorems. So I'll show you again this table, which corresponds to some parameter space for classical de Sitter solutions. And as I said, in this remaining corner, we could not find really classical solutions, but maybe there is a reason preventing us from doing this, but it's not so clear why we did not succeed. And there is no no-go theorem formulation of this really. So here we're rather focused on the rests of the parameter space. So all the places where you have a cross and where you have a clean no-go theorem. So I rewrite the same table here, and I give numbers to all these no-go theorems, numbers highlighted here in blue. Each of these numbers is a no-go theorem, and the entries here in the remaining corner some further constraints requiring some necessary ingredient for de Sitter, like for instance the Ramo flux to be noted. Now the whole work is to put these various no-go theorems in some Swampland format, some Swampland conjecture format, to compare it to the previous conjectures. So let me give you a concrete example. So let's take this no-go theorem number 2, which works for p equals 7 and 8, or p equals 4, 5, 6, and the absence of this Ramo flux. So these are the assumptions of the no-go theorem. So you can start in 10D with type 2 supergravity equations of motion, and you can combine them in some manner to get an interesting expression for R4. As you can see here, R4 is actually negative. Indeed, it's given by minus a square, and here minus a square. This is true if this coefficient here is positive, and this is guaranteed by this assumption, actually. So provided this assumption is there, then R4 is negative, and you conclude that you cannot have de Sitter here. That's the no-go theorem. Now you can derive the same thing in 4 dimensions, provided you have a corresponding potential. And here, a potential depending on 2 fields rho and tau is enough. Indeed, you can find a combination of a potential and 2 of its first derivative to give exactly the same combination. You can see it's the same combination, except that now you have a dependence on tau and rho, because this is done off-shell. Actually, if tau and rho are equal to 1 in our conventions, we are then at the extremum. And in that case, the first derivative vanish, and you get precisely the same equality as before. Now, the good thing is that this is also valid off-shell. You still have the inequality. And from this, you can bring this to what I call the Swampland format, which is you can prove that from this inequality, you can get that inequality on the gradient of the potential, where the C number can be obtained from the numbers here in the combination. Okay, so that's how we proceed. Well, now let's look at the number, actually. Well, you can verify that this is actually equal to square root of 2/3 for p equal 4. Otherwise, this is bigger than square root of 2/3. So here you should be puzzled, at least I was very puzzled, because this is precisely the TCC bound. And from this perspective, there is absolutely no reason to get this number. I've just played with supergravity, either in 10 dimensions or in 4 dimensions, and I get out precisely this number. I haven't done any quantum gravity argument on trans-Planckian modes. I haven't taken any limits. I haven't done any averaging. So it's quite amazing that I get this number. Of course, from a Swampland perspective, it should all work, because supergravity is a quantum gravity in some limits. So of course, then it should match if the conjectures are true. But at first sight, it looks quite surprising. So, well, then we verified this for all the 9 or 10 other no-go theorems. And we did this in detail in that paper. So these are the various no-go theorems, these are the various assumptions, and these are the various C numbers that we got. As you can see, the TCC bound is actually always satisfied, and several times with saturation. So for us, it was a nice surprise, and we actually get a quantitative verification of the de Sitter Swampland conjectures. And it remains still surprising how well this is working. So in a sense, we prove these conjectures in this part of the parameter space. Now, there is still this remaining corner of the parameter space where there's a failure to find classical de Sitter string backgrounds, but it's not clear why. And therefore, this question remains open. Okay, to go a bit further still, this, I think, gives us confidence. At least for a minute, we can trust these Swampland conjectures. And therefore, we may ask ourselves, well, is this hinting at a deeper reason for this obstruction of de Sitter solutions? And as we said already, all the Swampland conjectures are thought to be related. There's actually a web of Swampland conjectures. And so what came to our mind is that, well, maybe we could translate the impossibility of getting classical de Sitter to another conjecture. And well, we thought of this distance conjecture because there were already several proposals in the literature that related to the distance conjecture. And but in addition here, we were interested in the distance conjecture because the distance conjecture also involves a large field limit or large field distance. And interestingly, it also has a parameter lambda, which is of order 1. So we then thought, well, if we can put a bound on this C parameter as proposed by the TCC, then through the web, maybe we should be able to put a bound on lambda. That was our reasoning. So we then looked at many examples and very nice checks in the literature, and I apologize for not giving the appropriate references here. But there's been very nice pieces of work about this. And we also did some quantitative tests of the distance conjecture again. And well, given all these examples, we could verify and propose the following bounds, that lambda should be bigger than a certain fixed number, lambda 0, which is a half of the square root of 2/3. In other words, lambda 0 is a half of C0. I think that's the number which was given in the talk by Cumrun Vafa also when he was talking of a relation between the conjectures. Well, to justify that such a bound should actually exist on lambda, we then propose a generalization of a distance conjecture, which would then naturally lead to lambda being bounded, because in the standard form, there's no reason for lambda to be bounded. So I don't have time to specify this generalization here. Then this could justify that there's a bound on lambda. And another thing we wanted to justify was this value and the relation to the value C0 that appeared in the TCC. Therefore, we proposed a relation between the two conjectures, saying essentially that the mass on the one side should be related to the square root of a potential on the other side, up to some constants. And the square root of the 1/2 here is the 1/2 which appears here. So this justifies this value. So this way we could translate the claim of a node de Sitter into some asymptotic bound on M and on lambda. And it offers a new perspective on then this question from the Swampland from the Swampland program perspective. Okay, so okay, here is the summary of my talk. Maybe I will skip it and just leave it open, and I will just go back to this initial question: do classical de Sitter string background exists? As you have seen, the tendency is towards the no, but it's not fully established, especially because there is this remaining corner that we still have to investigate. The reason is also not so clear why there is such an obstruction against de Sitter, but hopefully in this talk, I've highlighted some directions where to make progress, and I think there are more ideas on the markets. And I think this is a very important matter, so I'm quite excited that it's quite active. Thank you very much for your attention, and I just flash back this in case there are questions. Thank you.
Thank you, David, for a nice talk. Are there any questions?
I can ask a question, maybe, yes.
Sure.
So there are in principle also other de Sitter constructions that include non-geometric fluxes, which we don't understand really well and don't control, which include NS5 branes, which include fractional Stern-Simons invariants, which include KK monopoles. And then you can, of course, just start with compactification on spaces that immediately break supersymmetry. So I think to some degree, we're only testing a small part of the classical landscape, or not, or would you disagree? Or?
Yeah. Well, yes and no. I'm not sure about non-geometric fluxes. This is a tricky one, of course, because saying this is classical string theory is a bit tricky.
Okay, but then throw out the non-geometric, yeah.
But including NS5, including KK monopole, I agree. Including anti-D branes also. And to me, it's difficult to include NS5 and KK monopole because then you would need the equivalent of orientifals for those in order to satisfy some sort of tadpole for these objects. I'm not saying this doesn't exist, but having explicit compactification with everything, all these things intended is difficult. I mean, it's not so often that we see this.
Yeah, I totally agree. I'm just saying it's somewhat a search under some lamppost to some degree, right? Unless we establish that all these other things don't help, or
yeah,
I mean, maybe by some duality you can say I can somehow map this whatever D brane to a KK monopole or something, but combining all of them seems right now out of reach, and it could potentially be that something is lurking there, but who knows, right?
This is true. However, this is true. There's a lamppost. However, I think if we get a definite results in either direction, it would still be a good progress in the sense that if in this, let's say, restricted classical framework, we do find an actual classical de Sitter string background, that would be a great advance.
I totally agree.
And on the other hand, if we make all these no-go theorem quite precise, and I think this matching with this number of the TCC is also a progress, and maybe we could then, I don't know, more or faster enlarge all these no-go theorems to these other cases that for now we don't include.
Yes,
yeah, that's the hope.
Yeah,
but,
I totally agree. Yes.
But yeah, thanks for the comment. It's true.
Okay, any other question? Okay, if not, let's thank David for a nice talk.
Thank you.
Thank you. So we'll close the session today.
And thanks, Dilip, for conducting this, and thanks to all speakers and participants once again, and see you tomorrow for Ashok's talk at 9 in the morning. Goodbye, and have a rest of the day very nice. Bye. See you soon.
See you. Bye.